Assay methods for vitamin D, an overview. Vitamin D is a combination of compounds, which consists of 9-10 secosteroids. The 10 secosteroids only differ in the structure of the side chains and are thus identified as a single entity since they are structurally related to 4-ring compounds, guanine. Vitamin D derives its photochemical reactions from this compound. D vitamins are unstable in acid solutions and stable in alkaline solutions. Further, they are reasonably soluble in ethanol, oil, and fats and highly soluble in solvents such as ether, methanol, and chloroform. All the D vitamins are highly sensitive to light, especially in the solution form. This, however, can be stabilized through the addition of vitamins A and E into the solutions. Since only a few foods contain vitamin D, the assay methods developed over the years strive to be sensitive, accurate, and reliable. Vitamin D assays are divided into biological and chemical assays. Biological assays are sensitive methods of vitamin D analysis capable of detecting 120 nanogram of the vitamin, while chemical assays are less sensitive and hence able to detect almost 9 times more vitamin components than biological assays. Gas chromatography is an exception to these two processes and uses an electronic capture detector that can detect as little as 50 picogram of the D vitamin. This technique is especially important to detect the vitamins, because vitamin D, just like vitamin B12, is a potent vitamin, with only a small amount needed in the tissues. Biological assays are the most accurate and effective vitamin D assay. Rat line tests. Here young rats have drained off their vitamin D reserves in the body, to the point where they develop rickets. They are then fed with vitamin D for 7 days after becoming rachitic. The shortcoming of this is that it is time-consuming. 25-hydroxy-vitamin D assay. This is a fairly new assay patented in 2003. The assay consists of processes where the 25-hydroxy-vitamin D is assayed from a blood sample. The pH is then lowered to 5.5 to disassociate the 25-hydroxy-vitamin D from the binding proteins in the vitamin. The next step involves determining the 25-hydroxy-vitamin D concentration in the sample. This assay method is distinct from others because it does not remove the vitamin D binding protein. As such, this assay provides a viable way of measuring both ergocalciferol, 25-OH vitamin D2, and cholecalciferol, 25-OH vitamin D3. Colorimetric assays. These are easy to execute but require sufficient vitamins in the test sample for the test to react. Insufficient amounts lack the sensitivity necessary to bring up colorimetric changes. The most important factor in this assay is the color reaction, which is made possible by the ring structure, which brings about vitamin activity. This assay, however, has several drawbacks, which include inadequate specifics, which makes vitamin quantification hard. More than this, the requirement of sufficient vitamins can pose hindrances, since, without them, a measurable color change may fail to occur. Protein binding assays. The most common is the 1,25-dihydroxyvitamin D, which involves partially purifying acetonitrile serum extract through column chromatography separation. The process is followed by liquid chromatography, which is done under high pressure. The results attained are then subjected to a protein binding assay. A receptor specifically drawn from a healthy chicken's duodenal mucosa is used in the assay. 2 milliliters of the sample are necessary to give the assay sensitivity of 17 picomoles per liter. This assay is rapid, technically simple, and uses a binding protein, duodenal mucosa, which is readily available from a healthy chicken. In addition to the binding protein being readily available, it is a stable protein for use as a reagent. Others. Throughout the years, researchers have developed several assays for vitamin D analysis. Colorimetric is one such assay that uses aniline hydrochloride and antimony chloride. This assay is primarily used to assess the vitamin D presence in pharmaceuticals and has a working range of 3.2 to 6.5 miles. Trifluoroacetic acid, ultraviolet absorption, is another assay that uses a vitamin D solution with 5.7 nanomoles and expects it to absorb 0.10 nanomoles at 264 nanometers. The advantage of using this is that the conversion of provitamin D to either D3 or D2 can be easily observed. Ultraviolet fluorescence assay is based on acetic anhydride sulfuric acid properties, which act by inducing fluorescence to the vitamin. Bioassay techniques used in vitamin D analysis have the benefit of being specific and sensitive. However, they consume more time, are expensive, and even the slightest form of contamination could alter the results completely. Regardless of this, however, Mcdowell states that the physiological effects of bioassays are quantifiable, while the effects of vitamins as observed in the assays are directly proportionate to the same in theory. Chemical assays, on the other hand, are less costly and fast, but have a higher probability of giving nonspecific results when compared with the bioassays.